Hey everyone, let's dive right into this explainer because we are about to unpack what is literally one of the greatest aha moments in the entire history of human thought. For centuries, mathematicians were wrestling with two giant, seemingly totally unrelated problems. They felt like completely different universes of math. But then, a hidden bridge was discovered, a master key that essentially unlocked modern physics, engineering, and our understanding of the universe. Get ready, because we're going to connect the two worlds of calculus.
So let's start with a really crucial question. What actually connects your car speedometer to the geometric area of a shape? At first glance, absolutely nothing, right? I mean, your speedometer tells you a rate of change, how fast your position is changing at one exact frozen instant in time. That's a concept involving tangents and derivatives. But finding the area of a weird curved shape? That's a problem of geometry. How much space is inside a boundary? For the longest time, finding a rate of change and finding the area under a curve were thought to be two totally independent mathematical puzzles.
To appreciate how wild this is, we've got to look at the old way they used to solve the area problem. To find the area of a shape with a curved top, what we call a curvilinear trapezoid, mathematicians had to use what we now know as Riemann's sums. Basically, you approximate the area by slicing the shape into tiny rectangles, calculating the area of each one, and adding them all up. You try to fill the space under the curve from point A to point B. You pick a point inside a slice, find the height of the function there, multiply it by the tiny width of the slice, and add them all up. But here's the catch. If you want the exact area, you have to slice it into an infinite number of infinitely thin rectangles, and then calculate the limit of that infinite sum. Calculating infinite sums by hand, it is an absolute mathematical nightmare. It's incredibly tedious, highly complex, and frankly, a great way to ruin a mathematician's weekend. It was a massive roadblock. Which brings us to our inciting incident. Is there a better way? Could there possibly be a shortcut? You know, a mathematical cheat code to bypass the whole tedious nightmare of the Riemann sum? Mathematicians desperately needed a way to find the exact area without having to physically add up infinite numbers of microscopic rectangles. Well, here's how they actually built that cheat code. Instead of looking at a static fixed area, they had this brilliant shift in perspective. They created the accumulation function. First, you graph a continuous function. Second, you lock in a starting point on the horizontal axis. Let's call it A. Third, and this is the genius part, you don't pick a fixed endpoint. You let the upper limit, x, vary. It can just slide back and forth. Finally, you define a brand new function, capital F of x, which represents the accumulated area under the curve from A all the way up to that moving boundary, x. Imagine that moving boundary sweeping out the area. That accumulated space is our capital F of x. Now, imagine we push our boundary x just a tiny, tiny bit to the right by a small amount we'll call delta x. That creates a super thin new strip of area on the edge. That thin new slice is the change in our total area. We call that slice delta F. If we really zoom in on that exact edge, that vertical strip delta F is so incredibly narrow, we can basically treat it like a simple rectangle. The width of this rectangle is our tiny step forward, delta x. And the height? Well, it's just the height of the curve right at that specific point, which is our original function, little f of x. So geometrically speaking, the tiny change in area, delta f, is roughly equal to the height, f of x, multiplied by the width, delta x. Okay, here is where the magic happens. This is the climax of our mathematical journey, known as Borrow's theorem, or the second fundamental theorem of calculus. If our change in area, delta f, is equal to f of x times delta x, what happens if we just divide both sides by delta x? We get delta f divided by delta x equals f of x. If we take the limit as that width shrinks all the way down to 0, we are literally calculating the derivative of the area function. And the result? Capital F prime of x equals little f of x. The rate of change of the area is exactly equal to the boundary curve itself. It's like a giant puzzle finally snapping together. This quote from the MIT OpenCourseWare materials perfectly captures the sheer magnitude of this discovery. Both fundamental theorems say that differentiation and definite integration are inverse operations. Each undoes what the other does. This is the grand reveal, folks. The problem of finding a tangent line, differentiation, and the problem of finding an area, integration, are exact inverses. If you integrate to find an area and then take the derivative of that area, you end up right back at the original curve you started with. This realization absolutely changed the game. We could finally leave behind the old way, painfully evaluating definite integrals by calculating infinite sums of rectangles. We officially entered the new way, using the Newton-Leibniz formula. Because the area function's derivative is the curve, it means the area function is simply the antiderivative of the curve. This completely freed mathematicians from the burden of those complex sums. And here it is in all its glory, the Newton-Leibniz formula, also known as the first fundamental theorem of calculus. The integral of a continuous function, little f of x, from point A to point B is simply equal to capital F of B minus capital F of A, where capital F is any antiderivative of the function. To calculate the exact perfect area under a complex curve, you no longer need an infinite sum of rectangles. No way. You just find the antiderivative, plug in your endpoint, plug in your start point, and subtract. Boom. It is breathtakingly elegant. Now let's ground this in the real world. Let's go back to our car. Your speedometer represents the derivative, right? It tells you your speed, which is the exact rate of change of your position at one specific instant. But your odometer? Your odometer is the integral. It represents the physical accumulation of your distance traveled over time. Think about the physics of the theorem for a second. Imagine you're on a road trip and you obsessively check your speedometer every single second. In that 1 second, your delta t, the distance you travel is your speed multiplied by 1 second. If you add up all those 1-second distances over your entire trip, you're basically calculating a Riemann sum. It's an approximation of how far you went. But the fundamental theorem of calculus guarantees us that the exact integral of your speed over the trip is flawlessly equal to your final odometer reading minus your starting odometer reading. Integrating your speed perfectly outputs your accumulated distance. And it's not just motion. The same exact math allows us to calculate the total work done by a varying force. The math directly governs physical reality. So we started with two totally distinct puzzles, calculating the exact moment of change and calculating the vast accumulation of area. The fundamental theorem of calculus proved they are simply two sides of the exact same coin. Which leaves me with a final thought for you to ponder today. If the geometry of shapes and the physics of motion are so elegantly, perfectly intertwined by this invisible mathematical thread, what other seemingly unconnected forces in our universe might actually be beautiful, hidden inverses of each other? Thanks so much for joining me on this explainer. I'll see you next time.